All right, welcome to GlobeBusters Season 14, Episode 11. We got Paul from Playing Reality here, ready to do his Horizon presentation, Part 2.
Yeah, how are we, guys? How is everyone?
We got Alan in voice, but not picture today.
He's
Somewhere.
incognito, lagging.
All right, so Alan may or may not be here, but that's all right. He's here in spirit.
Sorry, my internet's lagging. Or lack thereof internet, I guess would be a better way to say it. But welcome, everyone. Thank you for the intro. Paul's going to be picking up, doing a little recap from what he did last week to touch base, give us a little refresher. And he's going to be jumping into some refutations to some of the common things that the Globe lads put forward to try and refute what Paul is putting forward. So whenever you're ready, good sir, go ahead and start the screen share.
Okay, let's get over here. Is that now sharing? Can you guys see that? Oh, I don't see it popped up here. What's going on? Oh, there we go. So yeah, you guys can see that now.
There we go. Sorry, I was on mute. Perfect.
Okay, so he'll be getting back into it. I'm just going to do a quick little recap of what we went over the other day, just a very mild one, but going over some very important points again, things that we really need to pay attention to. And this is where we need to really start focusing on. And I'm probably going to need some of you guys possibly to help with math and stuff like that, so we can get some other people not being so upset with us that we don't have the math involved. This was actually a pretty interesting observation. This thing here, there was nothing there. I don't know what the hell this was on this day. There was absolutely nothing there. It was like a massive container just sitting there. Really weird. So I don't know. But okay, so the horizon is the dividing line of perspective. The horizon is the furthest visual point where we can see the surface. It is the furthest visible boundary where the sky appears to meet the ground or water, and all visual paths converge to a vanishing point. It's where convergence ends and divergence begins. Okay, so again, you are the dividing line of perspective. As always, I'll always mention to everyone, sub to these guys if you are not already. Right. So we're going to just go over this part here again, because this is really a real part of the main argument. Now, as something moves away from the horizon, it will disappear from the bottom up. As it moves back towards the horizon, it will appear from the top down. This is the one thing that we really need to get in. It doesn't matter whether or not it's beyond the horizon or whether it's in front of the horizon. They are all doing the same thing. All right. So we went over this, where this one here, I'm just lowering myself. And as I go lower, we see them doing the equal and opposite thing. Now, the one very main point that I didn't mention the other day was that because I am putting myself in front of the horizon and we're looking at what's going in front of the horizon, then we are negating refraction. So refraction is always going to be there no matter what. But by looking in front of the horizon, we're not really worried about that. We don't have that extra distance going on. Now, as something gets closer to the horizon, obviously refraction starts to kick in a bit more, but it doesn't matter. This thing that we see here of this equal and opposite reaction within the horizon. So from either side of the horizon, we see the exact same thing, right? But we know that on our side of the horizon, what we're actually looking at is a boat, a ship, anything, whatever it is, just obeying perspective as it moves towards the horizon. And we're getting the exact same thing beyond the horizon. Now, in front, we really need to focus on the fact that this has nothing to do with refraction in front of the horizon. Okay, so when people are trying to gaslight us, and we've been sitting there trying to work out all this refraction crap going on beyond the horizon, we don't need to worry about that with this. because we're looking at what's actually happening in front. Okay, so as a ship or boat or anything goes off, so we're looking at it from a front perspective, and they're looking at it from their personal side perspectives, and they're actually looking forward. And as they do this, we're looking at it from as if we're watching it from the little dude on the right. He will see it go down, and as he sees it go down, she also sees it go down towards her. So both of them are watching it go down. It is all just perspective. Again, this one here, as we watch the boat come forward away from the horizon, because that is the important point here, it's moving away from the horizon as it comes towards you. The big ship is moving away from the horizon as it moves away from you. We are seeing this same thing. We really need to, this is something that really needs to get into our heads. It's obviously, it's a new concept. People haven't seen this before, apart from when I've presented it in the past, but I never presented it quite as detailed as what we're looking at now, because I didn't have all the different, it didn't click to me that this is what was going on until I was sort of doing those presentations. And then I started filming all these different ships and boats going from horizon to horizon, gathering the evidence basically. Okay, so again, does this remind you of anything? All the difference is, so if we go back here, the difference is that when something's in front of the horizon, we're going to watch it get larger as it comes closer to us. When it's on the opposite side of the horizon, it's going to get smaller as it moves away from us. But the effect is the same. We're seeing the same thing, right? And that's why when I put the water over the top of it, we'll see the sail disappearing as it comes closer towards us. Okay, so I'm not just randomly putting water here. Here is where the water line is. We see the water line here, and it's progressively getting lower as this gets closer to the horizon. Okay. And so when we see a ship come from beyond the horizon and come towards us, we see it rise up over the horizon. Just as we see here, as a boat moves towards the horizon. So both of these boats are moving towards the horizon, and they are both doing the same thing. They are both climbing up or appearing to rise up over this horizon. They're doing it in exactly the same way, exactly as I showed in, if I skip back here, right? They're doing this. This is what they're doing. We are seeing this, right? One is coming up, the other one, no, they both appear to be coming up, right? So let's just skip through here again quickly. So both of these two things are doing the same thing. There is no difference, except this one's coming closer and this one's moving further away. That is the only difference between the two of them. Now, is this something that happens all the time? Would this happen every single place in the world? Of course it would. Perspective exists everywhere in the world. So there's no time that anyone could ever film a boat coming towards them from the horizon, moving towards the other horizon, that this won't happen. This will happen for everyone, everywhere in the world. This is not just something that happens for me. This is something that will happen for every single person in the world. And you can go out and you can do this yourself. You can film a boat. If you don't want to film it the whole time, you can just take photos of it, put them together, make your own little GIFs. But you'll see every single time something is moving towards or away from the horizon, it's either going to appear to drop below the horizon, or it is going to appear to rise up as it gets to the horizon. And this happens with absolutely everything. There is nothing that we have or that you will see that doesn't do this. Okay, so if we're looking at this, if I can grab a little bit of audience participation from one of you guys. If we look at the left one, the picture on the left and the picture on the right, which one would you say is closer to the horizon?
Right.
Exactly, right? And we know that because we can see that we can see where the horizon cuts through it here. So this is telling us that this one is closer. This one, we have the horizon up higher, and now this one is further away, closer towards me. As something moves closer to the horizon, it will begin to rise up and appear as if it is coming up over the horizon. So this is that same boat. I'll just skip through it because I'm not going to play the whole thing. So here, as it comes forward, we see it slowly, progressively getting lower and lower on the horizon. I was trying to keep it all in one focal length, but that wasn't really working. I should have changed focal length. But now we will see it start to rise up again until it reaches its furthest point. And as we can see, it didn't quite fully reach the horizon because the horizon this day was closer to 9 miles away. So it's not going to fully reach the horizon. Now it came back towards me, and we see it doing the same thing
Well,
as
I
it
don't
goes
know.
all the way.
You know, as a devil's advocate, what I see is Earth curve coming up and obscuring the bottom of that ship in equal proportion at exactly the same linear rate as it sails into that horizon. So how would you convince me otherwise?
We'll go into how the flatness that we'll get on each day. So for me, the way I would look at it is what we're getting is the horizon coming closer and further away from us. Now, they're going to say that these things are due to Earth curve, but they need to point out where in Earth curve. How are we getting jetties, etc., being more like 20 feet hidden when their globe says only about 4 feet, when all they've ever argued is, will refraction lifts things up over the horizon. Okay, but refraction isn't lifting anything up over the horizon. Refraction is just extending the horizon.
That's precisely the direction I like to go in conversations like this, that people talk about the refraction or the curvature of the Earth that you're supposedly going over in this really immediate horizon. Yet at the same time, we're looking at Steel to Mike Tyson and everybody talking about jets that are 40,000 feet in the air. And you don't see any kind of curvature like that. If the Earth were this curved, the Earth would be no bigger than the state of Texas.
Well, right. So that's it. Because that's the meta argument right now is the Globers would argue that what you're seeing is the consequence of a physical geometric Earth curve, which is in accordance with, a sphere of radius 3959, which ends up being using the Pythagorean theorem for like a 6-foot observer. They say this ends up being the 1.22 times the square root of the observer sight in feet. That's how far that physical horizon is away from the observer, right? When you do that calculation, and you're trying to.
That's exactly
Right. So, and then what our argument though is that actual line, which by its definition is the apparent place where the sky meets the horizon, right, is not the result of a physical geometric curve, but an optical phenomenon that changes with, as you're pointing out nicely, observer height. But so now the two positions are: is that a physical geometric position or is it an optical phenomenon? And when you offer evidence that it fluctuates in accordance with optical phenomenon, then they adjust their position and they go, well, it's the optical effect of a physical phenomenon, and that's the current Glover position.
Yeah.
Okay,
Yeah.
so that's where the argument currently is, where they go, yeah, it is a physical actual place at that exactly 1.22 times the square root of the observer sight feet away from me, but it's fluctuating wildly because of refraction and other sense, and I get to get my cake and have it and eat it too. That's kind of where we're at.
Yeah, where in reality what we actually have is a flat plane, and within that flat plane, when we have the horizon brought closer to us, everything beyond it starts to disappear. So no matter what, that's why I call the horizon is the dividing line of perspective, because no matter where that horizon is, so if it comes, like if I'm at say 20 feet as I normally am, if I was to actually get that horizon come to 1 mile away, which would be insane refraction, like I've never seen it that close, about 3 miles, maybe 2.5 at the most, or at the closest is what I would see it. But let's just say it did come to 1 mile away on another day, everything would start disappearing from 1 mile away. because the horizon is the furthest point that you can see the surface. So no matter where that horizon is, whether it be 1 mile away or whether it be 100 miles away, we now have the dividing line, and your perspective will change, and then we flip to the opposite side of the perspective and we go into divergence rather than convergence. So where everything converging up to the horizon, and once it hits the horizon, everything will diverge away from the horizon.
And when we're looking at anything other than a temperature inversion at the surface, this refractive math that the globies keep coping with is actually serving to work against them, mathematically speaking. They talk about how things are appearing higher because of refraction. That allegedly it's light coming towards you is being pulled down to the denser medium so that you see things farther away, apparently higher against the quote horizon, where here everything's disappearing. It's exactly the mathematical opposite of what they claim refraction is supposed to be doing for their argument.
Yep, for sure. And then, we have the laser observations. Every single laser that we've ever seen bends upwards. And there was one, because like I say, a superior mirage. They tell us that a superior mirage is caused by the actual light bending down around the Earth. Now, we do have physical evidence, which I can't present because it's not mine, and I've been asked not to present it. The person will be presenting it at some stage soon. But we have physical evidence of watching a laser go through a superior mirage and going up, not down. You can literally see the laser going up. It's insane. You see it go up and then kind of straight, and then it goes up again and then straight, and then goes up and goes straight out and then starts bending up. You can see it covering the distance, and it's going up, 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 and then out. So their whole idea is that within a superior mirage, that light is bending down. Well, that's wrong. And it's been proven wrong by the only time I've ever seen anyone who happened to have shone a laser through a superior mirage. So when we look here, and we were talking before on how, sort of almost 90% of this space, 80 to 90% of this space is taken up within the very first short period. Now, this is 1 minute and basically 6 seconds. If we look from where it started moving away, it took 1 minute and 6 seconds to get to here, and it's taken up all this area. Now, the next 3 minutes, it took another 3 minutes for this to get to the actual horizon. So there's all that extra space there that we just can't tell because it's all compressed. Now, this was obviously my observation on the day, where I basically showed exactly what I've been saying, where on my side of the horizon, I'm watching perspective go up. Once it hits the horizon, and then when my friend eventually found it, and I'm showing the actual, I gave him a GoPro, and this was them on the boat. And unfortunately, I didn't realize I should have zoomed my GoPro in, because I was hoping that we would see the horizon moving away, but it was zoomed out too much. So that's just first time experiment or observation jitters. But yeah, so you can see here, as they're moving here, they can't actually see the jetty, which is where I didn't realize that they wouldn't be able to see the jetty. So what he did is he went way out to the left, because that's where his GPS told him to go, and then he cut down. So we kind of lost him. But next time we do this, he's going to map it out so that he can just go straight from jetty to jetty, so we don't have to try to find him. Now, as we went here, eventually my friend found him there. He's now on both of our horizons. He's starting to disappear from me, and then it will hit my friend's horizon. And now it starts to come down from my friend. I apologize once again. He's not used to this at all, so it was very blurry. He didn't know how to get the camera focused. But we now see on his side of the horizon, it started to go down. And you see from me, right here, it's now disappearing. And look where he's cutting across here. So now it starts to disappear. It heads down on the horizon for him until it gets to a point where we see it well below his horizon. We see this huge gap between the roof and the horizon here. And if we actually put this boat on top of this boat, you'll see that two boats, and it's coming up here somewhere. And then wait, that's not gonna grab. Anyway, so we've seen that. Right. So when I put that forward before in my very first presentations, obviously I didn't have this evidence. to back what I was saying. I knew it was going on. I could see that that's what was happening, but I didn't have that same evidence to back it. But now, obviously, we have the full-blown evidence to back that this is exactly what is happening on either side of the horizon. That when you get a horizon, the horizon divides perspective. And as it moves forward, now all of a sudden, we see it appear there for me. Right about there is where I caught it. Okay, so as it comes closer to me, he's watching it go up onto his horizon, to the top of his horizon, and I'm now going to watch it come down where he will eventually lose it. So this isn't really, we could form, I guess, a formal theory out of it, but when I say it's not a theory, I mean just like a normal sense of the word theory. It's not a theory anymore. It's basically a proven idea. It is a proven theory. And this will happen every single time without fail.
Yeah.
So next time that you're out there on the water, I guess should say, because you're down south like I am, spring's coming. And I think priority should be put on getting back out there on a nice, dry, clear, warm day.
Yeah, that's what we're going to
where
do.
the seeing's much better. So there's less ambiguity about the images that you're taking. That would be really good to see.
Yeah, well, I kind of did want to get out there. I'm getting out there on both types of conditions, because that one there, I wanted to get the conditions where the horizon was going to be between us. So on a really nice, good, clear day, we're going to be able to see from jetty to jetty. And when I film that, if he starts at me and I'm on Brighton jetty, what we're going to do is we're going to witness him not pass any horizon, because we can see from jetty to jetty, but I will watch him go up as he gets closer and closer to the other jetty, and my friend will watch him go from the highest point and watch it come down. And we're still watching the same thing. We're watching that perspective.
In that case, you're looking at about 6 miles between the 2 points?
It's 8.
8 miles. Okay, so maybe you should find 2 that are 12 miles or something for the dry, clear day.
Yeah, that would also be good. Yeah, I can try and do that.
That'd be the way to go.
I'm going to have to head down to Hallett Cove, where we can see. I'll see if we can do that. It's just going to be a little bit harder for the guy in the boat, because now he's going to have to do more like about a 12 to sort of 13, 14 mile journey. So it's going to be a little bit more work for him, and he's going to have to. It's going to be another teething problem. So he's
extra fuel. Give it a go, man. See what happens.
Yeah. Well, in a boat that size, it's a few $100s worth of fuel, so it's not a cheap exercise. Okay, so here we went back into the idea of when we're perfectly in line with any surface, we don't see the surface. All you see is a line. So if we were perfectly in line with the actual horizon, as we are in the little helicopter here, we put his eye line right on the horizon, he can't see any surface. So as we discussed last week, how are we going to get this to happen? How are we going to get this ramping up at the horizon, or this visual ramping up at the horizon? Okay, so we're back here, we put our boats in, and we want to get these boats to obey this perspective. So we want them to be doing this, going up, as we know the horizon does. And as we discussed last week, the only way that we're going to get that is by rising up. So it's your actual height above the surface that creates the horizon in the first place. That's what actually creates our horizon. Because if you don't rise up and you're perfectly in line with that surface, you are not going to get that ramping. You're not going to get a horizon a distance away from you, because the horizon is going to be right in front of you. Now, we could just say that this rising up wasn't this high. We could replace this and say he only went up 1 millimeter. And now we've got a little 1 millimeter visual ramp there. So no matter how high you go, you're going to get this perspective. All right. So then we go up, and as he goes up, perspective changes for the clouds, for everything. Right. And then we get back to this point where we will see this, the perspective of everything and basically the clouds would end up becoming the ground, and then the next cloud layer would become a cloud layer, as it already is.
Exactly. The animation that you're showing right now goes to Dubé's original point. Briefly put, succinctly put, that the horizon line itself, the apparent horizon line, comes up with your eye. And down with your eye. Yeah.
And now let's say that on a regular basis, it is dropping a little bit. Well, who cares? That's refraction. So it could be a little bit higher, it can be lower. As you go up higher, if it's still dropping a little bit lower, it's still refraction. No matter what's going on, it's refraction that's going to be bringing that horizon closer to us. And so as we showed last week, as you rise, the horizon appears to rise with you. And we know that it's not physically rising with us. It is just apparent. It is how we see, and it is why we get that ramping of the horizon. Excuse me for a second. Okay. So this ramping up gives us what I've labeled the cone of perspective. And like I said, I think this is where technically people were getting confused about concave Earth, because we get this apparent rising of the horizon, which gives us a 360-degree circle around us with almost a 360-degree apparent visual ramping up. So we get this cone, and a cone basically is concave, right? So I think this is kind of really where the concave Earth is getting a little bit mixed up, because we do get this apparent visual perspective as if we're in a basin. Then the higher you go, the bigger the basin is. But it's still just extending over a flat plane. No matter how high you go, it just extends, because all raising up does is extend the horizon, and you just see further. Now I changed the colors of this for you, Stone. So as you move, your horizon moves with you.
Oh, fantastic.
Nice.
Far more
See that
visible.
better?
Way to go, man.
No worries.
Yeah.
So yeah, as we move, the horizon moves with you. Every time you move forward, the horizon follows you. Right? So your 360-degree circle is for you. And maybe I could say for you only, but if you've got a friend who's standing right next to you, he's in that same 360-degree circle. If his eye level is the same height as yours, then he's got that same circle. But he's in that same central point. So you're going to have a very, very similar perspective of how you'll see. Now, is that what we see? Is that how this works? So when we move, does our horizon move with us? So looking from Glenelg back to Grange, we have the horizon is in a different position as we move forward. We went over this last week. So now looking from Brighton, we have a horizon that is around that 3.5 to 4 mile mark. But looking from, looking from Grange towards Brighton, we have about a 3 mile horizon. And again, these little points here, these markers right here, are 3 miles away from me, or very close to, right? Because my buoy used to sit around about here. My buoy would have been just inside this. The buoy was just inside of these, and the buoy is 3.6 miles, and these were closer. So my assumption, because if we look at other pictures, you'll see that the buoy is probably about a few millimeters in front of this. And that few millimeters after over a 3 mile distance is going to be a reasonable amount. So I'm just guessing at 3 miles. It's probably not perfectly 3 miles. It could be 2.9. It could be 3.2. But it's close to that. It's about as close as anyone's ever predicted where the horizon is to the distance of it. So I was on a thing the other day, and we were just like, well, how do you know? I'm like, well, that's 3.6 miles away. So if the horizon's cutting across that, the horizon's approximately 3.6 miles. Well, is it exactly? Well, I don't know. Show me one where you've actually got the exact distance to the horizon. Like, it's not really something that anyone's done before. We've all just basically had to guess, like, oh, that looks like it's closer. That's further away. We know that it's further away because if you can see the shoreline of something 12 miles away one day, and then you can't see the shoreline and the horizon is in a different position on another day, you know that it's come closer to you. But we never knew how far away it was. Whereas here, I have markers, 3 miles. These ones here are definitely 5.5 miles, and this is definitely 8 miles. So we have 3 different markers that when we see a horizon in between these, we know that it is between 3 to 5 miles, 5.5. And when we see it in between this here to this here, we know that it's between 5.5 to 8 miles. Can we have a random guess? Yeah, we can have a random guess. Is it going to be 100% right? No, but it's kind of better than what most other people have had. So we went over that, didn't we? How did I get
We
back there?
did. And you essentially proved the answer to that question with the video of your buddy in the boat going back and forth, simultaneously seen from both sides, both ends. That's
Yeah.
exactly what you visually proved on video live, point to point, is that yes, the horizon obviously visually does your cone moves with you as you move.
Yeah.
Pretty straight up.
And here I'm just moving from different jetty further down to different jetty, right? And the horizon is moving with me. Okay, so then that's what we could see. See, I've done the cyan there again, or whatever color that is. So we should be able to
Looking
see that
good,
again.
man. Looking good.
Yeah. So each one of those, you'll see where it says Grange. That's where I'm standing on Grange Jetty. And then I move to the one which says Glenelg, and then move to Brighton, and then move to Kingston Park. And each time the horizon moved with me. And then we go to this day, and now we can see actually all the way to the jetty. We're seeing all the way down here now. These are those same markers that when I'm looking from this jetty down, these are the markers that were 3 miles away, and now they're 5 miles away from me. This here is something that we will look at in a moment. This is the part of the next presentation. So this is an inlet for an area we call West Lakes, and they bring salt water from here into West Lakes. This is 8.5 miles away because, in fact, it's 8.5 miles. So it's basically half a mile away from Grange to there. Grange is 8 miles. And looking back, here's those same poles at the 3 mile mark, poles at 5 miles, jetty at 8, and we're seeing down to the shore. So we're actually seeing this is just under 9.5 miles to here. So we want to get one on this day. This is the day the next sort of observation that I want to do. But I want to try and get a few of those boat jetty to jetty or peer to peer observations. So I wouldn't mind getting, once we sort of get it right as well, getting a clearer one, so that I can have something clearer to present rather than having something that's all fuzzed out and blurry. And so then we have the difference between the 2 days. Here we have the closer horizon. Here we have the further away horizon. Perspective is going now all the way to this jetty. So if we watch that boat, I would watch that boat go all the way to the jetty. It would not disappear at all. Whereas on this day, we would have had the same effect. It would have started disappearing from here. And this is a pretty close horizon again. So by the time it got to that jetty, I wouldn't have probably been able to see the boat. And my friend wouldn't be able to see it to start with and start it until it started getting closer to the horizon. But here we would see it go all the way from jetty to jetty, or as you guys say, from pier to pier. And this is what we would have on that day.
That's because we just sound cooler than you do.
You sound cool. Well, we just like to go jetty. It's a jetty, mate. Pier sounds too snobby. It sounds like it should be something the British say. Just going to the pier. Okay, so here we have our cones of perspective, or from the plane. Anyone looking from here is looking down, right? Or here he's looking this way. We're watching this plane go up and back down again. And here we're watching the boats go from high to low. We're watching it go the opposite direction. So this is how our perspective works. And you're right in the middle here. So you're this person standing in the middle, and you are your own personal dividing line of perspective as well.
Precisely. The word crepuscular is coming to mind.
Yeah. So we're just then you would just do it so that crepuscular is the rays going down this way. So they're going that way. Whereas when you're looking up, obviously they're going that way. So here's where we'll start to get into the next point. All right, so here's where we're going to get into the next part. So from here, now, obviously, as we just discussed, this isn't really a perfect perspective grid, but this is just how they all get drawn. So each one of these could represent a mile, but in reality, we know that the first mile would be like up to here. But if we drew it that way, it just wouldn't really have the same effect. But so as we go through, and we'll see this come closer, when we draw a closer one, we'll see the horizon drop. So when we move from further away to closer, we are going to get a drop in that horizon. And each time we progressively move the horizon closer to us, to the point where if it was right at our feet, that's where it would be. It would be all the way down at our feet. So every time on a certain day we have the horizon move closer, this is what we're going to see. We will see the horizon dropping within our vision.
This is where we cue the globies to tell the joke about, oh, better be careful there because you might fall off the edge.
Yeah. And so when we get something like this actually shows us the drop in the horizon as it comes closer. Because this point here, as we know, the actual real horizon is up here somewhere. And it's not that it's up here somewhere, it's that perspectively, as we're looking in a perspective grid point of view, the horizon is going to be up here.
In fact,
Now-
on a clear, dry day, you could even draw it farther away than the ship you see. That,
yeah.
you know, if you could see farther, there would be a line above the ship even. If you
Yep.
could, with the ship, no difference in the distance that it is currently.
For sure. And then what you would have is your perspective grid would do this. And now that ship would appear like it has dropped from the point where it's on the horizon. So if it's on the horizon, it's going to be in the physically highest point in regards to the horizon that you can see. But if all of a sudden the horizon moved to, a few miles further away, now that ship would sit lower on a perspective grid. It would appear like it dropped into a lower position, but the ship hasn't dropped into a lower position. It's just that now that the horizon has moved, that ship is going to have to the entire scenery will readjust, and the scenery itself has to now change position or appear to change position because it's going to get lower in the grid. So if we put something here on this perspective grid, this is where it would appear. Or let's just say this thing here. If all of a sudden that little rock, whatever that is there, if the horizon all of a sudden moved to that rock, now that's where the horizon would be. This thing here would be starting to disappear below the horizon because all of a sudden the horizon's moved to even more miles further. This little point here would appear to be the highest visual position that you can see, which is the horizon. But this just shows you how when the horizon is in an apparently closer position, it will appear lower. Right. So when we're actually looking, and let's say we've got our little lassie here, she's looking straight across and she's seeing a horizon that's much further away. On another day when the horizon is closer to her, she will have a slight downward angle to look towards that because it's now closer. And on this further day is when we would have your Rayleigh's criterion and everything would kick in a lot more on this day, your angular resolution, where this is the sort of day where, like a small speedboat will completely disappear, but still actually be there, right? Where you wouldn't see it with your naked eye. You'd have to pull out your camera and there it is. Okay. But on this day here, you would still see the speedboat all the way to the horizon because the horizon is actually probably, 10 miles closer. But on this day, when you've got a horizon that's many miles further away, your little speedboat would completely disappear because it's just going to blend into the ground.
These are
You're not going to see it.
really good visuals on what exactly is happening, especially the bottom image where you're just apparently projecting it out as the cone you were so aptly illustrating before. but I think that what they argue is that, oh look, so if it's again a physical geometric point, and is that physical geometric point changing in these two images? Is that more Earth curve and less Earth curve, respectively, or no? And I think they're arguing that, like, okay, even though it's in the same physical spot, refraction and optic effects are making it jump from these 2 points. Even though, for me as a glober, it's at the same spot. The horizon's exactly at the same place in both of these illustrations that you keep flipping back and forth from, but it's only the optics that are making this physical geometric spot appear at different spots. That's what I have to argue as a glober, right? Like
Yeah.
my physical geometric horizon is still there where it always is, but you're just making it appear to be lower and lower. Tricky.
Well, it's like that. I mean, they're basically just going like, well, this is the real horizon right here. This is the geometric horizon. But we never see that. That's really rare. But so it's always going to be over like here, or it's going to be like over here.
It could be anywhere. Anywhere you see it, that's where it appears to be. How do you like that?
Yeah, exactly. But this is the real one. These ones aren't real. This one's not real. These ones are actually all just figments of our imagination. This is all refraction, but that's the real one.
Right.
Okay, so when you see it there, that's the real horizon. Everyone, let's all just clap now. Thanks for coming. We now finally see the real horizon. Like, it's just ridiculous. Okay, so this is where each person, this is what they're seeing. And we just watched that in that little boat observation, right? So she's watching the horizon come up. Now we can imagine this is our little gap here where we actually had our inferior mirage, and the boat was in the inferior mirage there for a while, and then it started coming back down again. Right? And this is basically what they're seeing, what I showed before. As it goes away, it comes back again. Okay, so here we have that inlet for West Lakes that I just mentioned before. Now, this is 2 different days. Right? So what's that? We have a completely different view from one day to the next. So what is this?
Earth
what is
curve
this gap
got a
here?
little wobbly, and it just appeared to jump, even though it's in the same spot every time. That's my position as a glober.
Yeah. Okay. So why is that like that? Well, that's distance. Right? So that horizon is at 3.6 miles away. This horizon is from 25 to 30 miles away. This is the land down there. So now I'm seeing all the way to the land, and that is up to 30 miles away, and I'm at a 20-foot observer height.
Yep. That takes us right back to the very famous Skunk Bay footage.
Yeah. But this is a nice clear day. This isn't crazy refraction. Look, this is actually nice and pretty clear all the way. So it's not like we're having some crazy refraction going on. You can see that there's no superior miraging. There's not like heavy distortion on this day. And so this is the equivalent of that. And then we go here is the equivalent of that. Right? So we have these 2 days of where we're seeing the horizon drop as it comes closer to you. And like I've put over on the left-hand side there, the perspective going back down again. So on that day, your horizon's at 3.6 miles away. The perspective from the person on the opposite side of the horizon, they're now seeing that drop. They're seeing everything now drop to their feet. But on this day, the perspective for anyone on that opposite horizon, they're not going to see anything dropping until many, many, many miles further. So pretty much what we've actually got in between that point and that point, we've got up to 27 miles of distance that is crammed into that little area. That's some pretty major compression.
I'd like to see some comparison done in terms of this proportionality that you're drawing here, weather type to weather type, across land, like on a salt flats or something away from the ocean, because here humidity is the highest and you're going to get the widest disparity between these two conditions, visually speaking. I'd like to see the same exercise done. I mean, you probably don't live near salt flats, so maybe you're not the right guy to provide the data, but we could definitely find somebody who is, probably in North America or Eastern Europe, where you just show up day to day, season to season, put your camera on the same tripod marks, if you will, drive your pins and come back to them in a month or whatever, or whenever the weather changes drastically. And I'd like to see that same proportionality done over land so that we can draw correlation.
Yeah, that'd be really interesting. Yeah, that'd be a great one for someone else to do. I think I've done my part here. Someone else can take that.
Oh yeah,
Someone else can take that bit.
you delivered, man. No question there.
Okay, so many moons ago, I had Zanuck send this to me and go, "Well, what's going on? What's happening? Why on one day are we seeing the distant oil rig lower than the other oil rig?" And the funny thing is like he's mentioned here atmospheric magnification, and I'm pretty sure that I've actually heard Zanuck in the past, and it might not have been Zanuck, it could have been Sly Sparkane. But I'm pretty sure I've heard one of them, and I'm sure it was Zanuck, say there's no such thing as magnification. But it's right there. You can see he's drawn like it's little boxes. But okay, so what's going on? All right. And I did answer this before, but now I'm going to do something that's a little bit more detailed because people still keep using this. And I don't know why people keep using this as to this is a problem for what's going on, because it's not an issue at all, because I basically just showed you, right? So let's just put these in here. And what we have is these oil rigs here. We have our dividing line of perspective, and all we've got is on one day on the left, our horizon is closer, and on the other day on the right, the horizon is further away. Now, actually, you'll see here, I'll just get out of there. We'll see here, I've drawn a line right here because this is actually an inferior mirage, right? So right there is an inferior mirage. So this here is miraging the top, right? So a lot of these people keep presenting us with inferior mirages, and I keep pointing them out. And then they keep saying to me, "Why are you obsessed with inferior mirages?" And I'm like, "I'm not. You just keep showing us stuff that's in inferior mirages
They
and
are
calling it Earth curve.
self-evident.
It's not my fault."
Well, they're really convenient for Earth curve, so I keep finding those when I look for my fictitious Earth curve.
Yeah. So it's like I'm actually having a whole thing with Earth is life at the moment over his observations. And I'm like, pretty much every single one of your observation is in an inferior mirage, in which he claims that not one of them is. So I'm now in the process of going through them, and I will show that all but one, and I suspect that that one is as well. The problem is that they're just really hard to see because he's got a lot of waves. And when you have a very wavy environment, it's really hard to actually pick the inferior mirage because the waves are breaking through it. So they're kind of hiding it.
I'm starting to think that's where Earth curve has been hiding the whole time within inferior mirages everywhere, and that's why it's been so
Predominantly.
tricky. Yeah.
Yeah, predominantly. And then what you actually have, and so what goes on is there's like an interim moment. So as the inferior mirage is building, before you actually even see the inferior mirage, the horizon is actually moving closer to you. And as it moves closer to you, things will be disappearing, but you won't see an inferior mirage yet. So now, as I've shown, the horizon being the dividing line of perspective, that as it comes closer to you, that dividing line is moving with it, right? So as it moves with it, everything in the distance starts to disappear and starts to appear to drop below that. And then all of a sudden it gets to a point where now the mirage starts to happen. But you get this visual point that as it comes closer, everything is starting to disappear. So it's looking, this is where you can have maybe a clearer horizon and things will be disappearing behind a clear horizon. But a lot of the time, it's actually in between an inferior mirage to what you would call a looming effect.
So with these two images side by side, and you've got your red box on the right half for the far platform, I'd be interested in just quantifying the images because they're obviously taken from the same distance away at the beach or wherever you're at. I'd like to see a vertical pixel count, box to box. You know what I mean? That makes it more real for people.
Yeah, for sure. These ones are from BLMS 69. They're his. These aren't mine. But yeah, so we'll move on now. So this is where we're seeing these two oil rigs. This is how we're seeing them, right? So basically, what I would put forward is that the point of where the light is appearing to deviate is where we get our horizon. And on the day when we see the oil rig that is now closer to us, the light is deviating at that point. And on the day where it's further away, the light is deviating from that point. So this is kind of what is creating the position of the horizon. This is what refraction is doing. It is bending the light up, which is the only thing we've ever seen with lasers. Now, some people would say, well, the lasers, you just don't see them when they're bending down. Cool story, right? That's all I can say to that is, yeah, good one. Good on you. Get out there and show it. Go a little bit higher, point a laser out, and let's watch that laser bend down. Because if you can't show a laser bending down, then you're not showing the direction that that light is moving. And you want to say your entire worldview is that the light's bending down. I don't want to see the light bending down in a fish tank. I want to see it bending down in reality over a long distance, because over long distance, we have seen lasers bending up. And like I said, I've now seen a laser bending up through a superior mirage, and a superior mirage event is meant to bend the light down. So that debunks that straight away. So here we have when it's the horizon is just coming to there, that is how we see. And as the horizon moves further away, this is what we see. Everything will obey perspective, right? Because from here, this one appears to be higher. The one that's closer to you is appearing to be higher because it's on the horizon, or it was actually just in front of the, or beyond the horizon due to the inferior mirage. But anyway, it's closer to the horizon, so it's appearing higher. But now when the horizon moves further away, it now is in a closer position. And because it's closer, perspectively, it now has to appear to drop lower than the horizon, because the horizon is the furthest visual point you can see the surface. So therefore, visually, it is the highest thing that you can see the surface, highest point where you see the surface. Now we go from here. We are going to now look at these observations. Now I'm using the buoy as the front to represent the front oil rig, and the jetty and the tower is representing the back oil rig. And what we see from the left image to the right image is that when the horizon moves, the entire scenery also has to move and change. So now we see that buoy being in a lower position. And if I just don't know if I put it somewhere, but let's just take where this buoy is here. If we were to move that here, that's up here. So we see this house here. We see where this is appearing to be. It's up here in this one here. But it's actually down here because the entire scenery has to change. The scenery can't stay the same because now the horizon has moved to beyond 9 miles away rather than 3.5 or thereabouts miles away. So the entire scenery must change and it must obey perspective. Okay, so let's go back into here. Right. So this is what we're seeing. As the entire scenery changes, we will see the equivalent of our oil rigs move. This is what we're seeing. Each time the horizon moves, we see more and more of the scenery in the background, and the perspective needs to change each time. So I'll escape from here. So here we see the buoy on the horizon. It's now in the visual highest point that we can see the surface. Everything from there now obeys perspective on the opposite side of the horizon, and it appears to drop. So everything is now dropping on that side of the horizon. It's not physically dropping, it's all optical. On this day here, the horizon is further away. So now we see the buoy has now dropped slightly below the horizon in front of it. And this is now raised up. It's not actually raising up. It's now the horizon has moved further away everything, the entire scenery now needs to adjust. This moves up perspectively, and now this all changes. Now we see the buoy here. It is lower. The horizon is now up here. And in fact, the horizon on this day was further than this, but this is 9.3 miles away to this point. And now we see the buoy well down here. The horizon is past the jetty now. So now the jetty becomes into the highest visual point that we can see.
There's a secondary effect here that I think we need to draw attention to as well. Left frame to right frame. Ignore the one in the middle for now. That when the seeing is poorer and the horizon appears closer, everything past it is so much more distorted, whether it's close to the water line or not. Take a look at that tower at the top, even. That, you know, when there's really poor seeing, everything is being distorted by the humidity and the conditions of the air between you and the object, as opposed to on the right, where the horizon is much farther away because the seeing is better and everything is less distorted. It's telling you exactly what's going on here.
Yeah, we have a pretty clear day all the way to the right. It's still pretty clear here. And, you know, and this is the thing is like, if let's say you only had a camera that could say do a 300 millimeter zoom or 400 millimeter zoom, all of these would look clear because you wouldn't see the turbulence in the air. But when you get it like because these are all taken at full optical zoom, 3000 millimeters with the P1000. So you're actually seeing the turbulence in the air a lot easier. Okay. And so this is what we're getting on each day. If we just put that buoy in line, we see how it's extending each time. We're now seeing further. And so this is another point that I kind of discovered or thought of, that what we're actually seeing here is the equivalent of each observer from each side. Now, I'll explain this because it could be a little bit confusing, but I'll see if I can get it right. So we see how here on this side, let's imagine that we're the person on the very left-hand side of the horizon and we're looking to our right. So let's just pretend that all of this is to our right-hand side. This one is low because it's closer to us. This one is high, or appearing visually higher. We know that they're not actually higher than each other. They're all on the same level, right? But this one appears to be higher because it is now on the horizon. This one is in front of the horizon, so it appears to be lower. Now, if we were to all of a sudden zap ourselves to the very right-hand side of the horizon, this here, see how now this would be the one that is closer to us? This would be the one that is further away. So to the person on the opposite side of the horizon, it would look like this. This one, which is closer to them, is lower. This one, which is further away, will appear higher. Exactly the same as we see it here. But the person on the opposite side of the horizon on this day would see it like this. Did that make sense? Or do we need clarification?
More or less. No,
Yep,
more or less.
I got you.
It's a pretty good point. Sure.
Yeah. So we're basically just seeing almost that perfect thing of perspective as what I've shown.
Symmetrical.
Like as if,
yeah.
it almost is in a way, right? Because we're seeing the same thing. This one is lower because it's in front of the horizon. This one is lower because for the person on the opposite side of that horizon, who is far over there to the right-hand side, looking to their left, this one is the first one that they would see. So this one is going to appear lower in their vision. And
Yeah,
this one will appear higher.
The word reciprocal is coming to mind.
Yeah. Right. So this here, in a sense, is also just showing us like a mirrored image in a point, like we just put the observer for this on the opposite side of this horizon. And now they'll see this. So they'll just be looking at the same thing. I just thought that that was kind of interesting on how that could work. But so here's what we're seeing on a day when we have the horizon that is closer to us, our visual point is only going to here. This divides our perspective. This is our horizon here. And from there, everything will appear to drop. And this is now no longer an idea. This is not something that I'm just coming up with. We just watched it in my boat observation, going from jetty to jetty or pier to pier. Right? We physically saw this happen. This isn't something that I'm just putting forward as an idea. We have now physically seen this actually happen. Now, right, so I don't know why I put that there. Let's go here, but here we have this where we're seeing these. So over here, I just placed this here as like this as well. So we just imagine like we've got this one here, and as the horizon moves further away, this is what we're seeing. They're just all basically the same idea. These things are all the same. As the horizon moves further away, everything in the distance now has to obey perspective, because when we see further, our horizon is now further away, meaning that it is now the furthest visual point. We can't see the surface beyond that. So this becomes the furthest visual point that we can see, and everything must obey the way perspective works, which means that we would put our perspective grid all the way to the horizon on this day, and on this day it would only go to here. So everything's got to change, and the entire scenery does change. I remember Sly asking me one time, are you trying to say that only the things in the distance are changing or whatever, or only the horizon's changing? And I'm like, no, the entire thing changes. So when we go from here to here, on this day, we have our perspective that would be dropping. And that's why we see the oil rig in the distance would be dropping down. And when we move to the other day, we would see it rising or appearing to rise. It's all optical. Everything we see is just purely optics. And then I just kind of put that there just to reiterate that fact. We don't have to fully watch that again. We just thoroughly went over that. But just to remind everyone that that's what's going on. We're watching it go up. Yeah, go Stone.
I think the problem is that you've done such a good job demonstrating this is what we see on a flat plane. But what they've done is they've convinced everyone that everything that you're showing is actually because of this fictitious, never before been verified Earth curve, and everyone just accepts that. And even more so when they do like theodolite observations, and they're like, "Look, based on the angular size of how far away I know that is, here's how much Earth curve is obscuring this object because I know the height." And they're discounting all of this other perspective. They can easily try to quantify the rate at which things are obscured past the horizon and find that it's the same rate at which they say things disappear at the rate of 8 inches per mile squared. Like, oh, go figure.
Yeah, for sure. And then, like, I just love kind of an observation like this, because we sit there and we look at this and we go, well, here's the horizon. But is this physically below that? Like, we know that this isn't physically below this line because it's right there. We can see it. And this is also the beauty, is that because what I've done is shown what's going on in front of the horizon is identical to what happens beyond the horizon, we can't claim refraction here. We can't go funky refractions going on, because this is what happens whether you're 1 foot above the horizon or 1 foot above the surface or 1,000 feet or 100,000 feet above the surface. This is what happens. And we can't claim refraction here. Refraction isn't making this happen. This is your height. This is your observer height above the surface is what creates this. Beyond there, then we can start mucking around going, well, what's the refractive conditions? This is what's going on here, blah, blah. We can start, having discussions about what's happening there beyond that, and this is where the gaslighting happens. But here, you can't argue refraction here. And here we physically are seeing this boat below the horizon. But we know that it's not physically below the horizon because we can see it. But now when something goes beyond the horizon, because this is our dividing line, we can't see through the water. So now we just go, well, what's happening back there? The exact same thing. There's no difference between the two, just that this would be larger because it's closer. And if this boat goes beyond the horizon, it would be extremely small. So it will obviously disappear faster and be harder to see.
Air opacity mixed in, pretty straight up.
So then we have this on the day when we can see further. And now we just have the entire scenery where we see all the way to the jetty. Right? And now if we were to have her vision of how this would be, she would be seeing it the other way around. So if we just sort of drew the arrow the other way, and now we're looking from her vision, this one would be lower and this one would be higher, just as we see here. So I'll zoom in here. This point here are these things. There's actually like a little reef thing just there, but the tide is a little bit higher and we can't see it. You can almost just see a little bit of water breaking on it just there. We now see that this is lower than the horizon. The horizon is up here. Right? So we see this is lower for her, and then these are all higher. So she's now seeing this appearing to go up. She's just seeing exactly the same thing as what this guy was seeing, but he was seeing it from this direction, and she's now seeing it from this direction. We're both looking at basically the same thing. It's just perspective. It's a ramping up of the horizon and then a downward, but it's downward for him. But if she's looking out, it's up. But if something's coming back towards her, it's down. If it's going away, it's up. So it's moving towards the horizon. It's going up. The same as like for him, if something's moving towards the horizon, it goes up. For her, it moves towards the horizon, it goes up. So he will see it come up above the horizon. So imagine my pointer, he wouldn't see my pointer right now. My pointer's a boat. As my pointer gets here, well, now it's starting to come above the horizon. Now he starts to see it until it gets here. They both now see it right on top of the horizon. And now she will start to see it disappear below the horizon, and he will see it come down towards him. It's not an idea anymore. It's been shown. And so on the further day, then she would just see all the way to the jetty, which is exactly what we saw here, where you can see all the way to the jetty. Right, so this is just what he's seeing, and then he's seeing all the way. Now, here's just a couple of blink tests, because they love the blink tests. And we see, as the horizon extends, we see perspective coming up there. We see the whole scenery change. So the inferior mirage obviously drops everything. But notice how it mainly just drops everything from around this point, and sometimes it's really only from around here. It's all within that band where everything's moving the most. We see magnification. So on this day, the tower is 239 pixels. And then on this day, the tower is 251 pixels.
You know I love it when you quantify stuff. Give me that. Yeah, yeah.
So I put a really crazy refraction one in one day on one of these. I'm not sure if it's this one, no. So again, we still see that dropping. You see it drop and raise. So all I did was line up these houses up here. Sort of lined up the houses higher up. So it all depends on where you want to line it up. If you want to line up the towers, the houses, it all depends on where you want to line this up. So here we have this day here. Right, and so we see the houses up higher don't really change as much, but we see the difference in the little umbrella section, raising and lowering more. Okay. This one here, I think, was quite extreme. Oh, no, this one wasn't bad. I think the next one I did was the really extreme one. So we go from there. Yeah, this one's the extreme one, I think. Just to, oh no, sorry, it's the next one. I'll get it right sooner or later. But we see the way that everything raises. Just the floor raises a little bit. It's not like the whole thing needs to raise up unless you get really crazy. Oh, maybe I didn't even put it in. Good job. But this is a further one away. So this is an area that's 16 miles away. This little point right here that you can see here, this is all the way to the shore. This is 14.3 miles away. And we see the whole thing change back here. This one here, we see quite a bit of change. Right, because this one is now more like 12.5 miles away. This is the point where I'm thinking I could go stone. I could go to this little area just here, point the camera back. It'll just be a little bit more awkward for the guy driving the boat.
Yeah, for sure.
So I have pretty good vision to this point. Okay. How many more? Okay, it's got a couple more. So here we see it again. And we see it dropping. So here we know that the light is bending up because we have the inferior mirage. But from what we've seen with lasers, light's always bending up terrestrially. I don't know, again, when someone can show us, yeah, there we go. I did put the crazy one in. So we get some crazy refraction. I didn't, did I do
there
it
you
there?
go. That's the extreme.
I think I did it on this one. If I line up these houses here and we watch how much we can get raising. But what we have here is we have a superior mirage right here. So you can see that this boat is just starting to come out of the superior mirage. Right here, this is a superior mirage raising all the water just here. So this is a pretty funky refraction day. And then that's it. So now we can land the plane.
Duck!
And that's it for this one. So if anyone's
There he
got
goes
questions,
over the curve. He's landing over the curve. Look at that shit.
Yeah. Yeah, if anyone's got questions, we can take some questions. Send in some super chats.
I
Give
didn't see
Cami
any
some love.
questions in the chat. Yeah, everybody's pretty happy with what they're seeing.
A lot of agreement, a lot of support. No questions that I was looking for. But I do love this prez. This is a really good one, man. I think that you visually demonstrate the things that we argue, which is what we see. Sure, we rationalize and we incorporate the same observations into different models. Like the Glober sees what they see and they go, look at how much Earth curve is there. Look at how wobbly the Earth curve appears to be at different spots. Isn't that wild? And we're like, no, look at how the horizon appears to move based on different conditions on each day. And we've worked that observation into our model. And what I used to argue is that the rate at which they quantify it is also indistinguishable, right? So under 100 miles, when they're trying to do parabolic versus linear versus spherical, they're going to come up with the same answer. So all these observations are below 100 miles. Literally, they've taken the quantification of it and they go, see how it proves a sphere? And it goes, well, no, it actually could either be represented linearly, parabolically, or spherically, and it would give the same result. But they ignore all that and they go, behold, Earth curve. Look, everything's a sphere. It's actually because Earth is a sphere. That's why we see that's why our perspective behaves this way, right? It's so sinister.
Break out another can of copium, boys.
Yeah. So here's that little thing at West Lakes there. So I've got a stack of photos of this. They're all at 1500 millimeters. Now, see on this one here, this is appearing to be almost our horizon, but the horizon is actually just up here. It's just that the sky and the water are very close to the same color. But we just watch the way the horizon moves up and down. And it doesn't really matter whether it's high tide, low tide. We can get a low horizon on a high tide. and a very high horizon on a low tide.
Imagine trying to substantiate Earth curve in that gray area in there between where the horizon line drops and changes intermittently.
Yep, and with every single one of these, when you see that horizon down low, we have an inferior mirage, which is dropping the horizon, and when you see it further up, that would be what would be classified as looming. But it's not necessarily looming. It's not coming up over a curve, which is technically what looming is referring to. Okay, so that is 71 days. I'm missing probably about 15 days that I haven't, maybe 20 days that I haven't put in here. We just see the way the horizon just moves up and down in this constant thing. So when someone goes out there with a theodolite and they are looking at these two different things, there you go. Look at these two. The tide is almost the same, and we see the difference in where the horizon moves. Difference between
They would argue
inferior
that,
mirage.
that both of those prove Earth curve to them. You know, they would quantify it both ways.
Yeah, of course. But you know, the whole idea is, where's it curving? We've just shown that this has got nothing to do with curve. This is all perspective, and the way that when the horizon moves, perspective must change. That's the thing, is that it's all perspective, and it's just like Nathan Oakley said many, many years ago, they just hijacked perspective and called it Earth curve.
Yeah, that's the basic.
But in some ways, we didn't know that perspective. What we were actually witnessing was perspective on two sides of the horizon. That's really the one thing that I've introduced that no one else has ever introduced before. That's kind of like the one thing that I've shown that has never been shown before, is that technically what we're actually getting is perspective on two sides of the horizon. It's like looking at this. We don't look at this and think that this here is actually below this here, because we know that technically this point here and this point here are the same. They're on the same level. But just visually, we see this well above this. But if you just now overlaid water over that and then put yourself to the other side of the horizon, well, let's just say you all of a sudden zapped yourself over there to the right-hand side of the horizon. This is all you would see. You wouldn't see any of this. All you would see is this top thing, but it would be much smaller than this and probably quite hard to see because it would be tiny.
Yep. I think we've always been looking at both sides of the horizon, but your visuals to actually separate it. I remember the first time you showed like Harry and Sally or whatever you named them, and they were on two sides of the same perspective, and you're just trying to demonstrate how, as one observant recedes and as one observed and approaches, they are just the same observation separated by the horizon. I think that's a really unique way to put it. That I think it took a little repetition for me to understand what that meant, and then just to realize that's what every observation truly is.
Yeah. Yeah. So when we're seeing, so like when someone's going, well, what's happening here beyond the horizon? Why can we only see halfway through this boat? Just post a picture of a boat that's in front of the horizon that's cutting halfway through the horizon as well, and go, why is the horizon cutting halfway through this boat? Why does the bottom of this boat appear to be below the horizon? They're just the same thing. They may not understand what you're talking about because they're going to go like, what do you mean I can see the boat, bros? But, you know, like that's why we've been gaslighted into just constantly looking behind the horizon, beyond it, because that's what we've been getting asked. We've been like, what's happening back here? But we have to go, I don't care what's happening back there. What's happening in front here? This is what's actually showing us what's going on back there. You can't just go, like, all they can really say is this is a coincidence. What else do they really have?
Well, they have to agree that those 2 points are equal altitude. I think that's what's crucial in terms of terminology.
Yeah. Either way, whether or not, like, let's just say someone's showing a boat that's half hidden by the horizon, behind the horizon, and you just show another boat in front of the horizon, you could technically be only 1 foot. As long as you are showing a boat that is appearing to be below the horizon, it doesn't matter. It's still the same effect, in the same sense of, you know, when I showed this. So looking at this thing here right at the very start. So when we look at this, like, I mean, these two things are well different in distance to the horizon and distance away. That boat there on the left is probably only like 600 or 700 meters, maybe a kilometer at the most away from me. And the one on the right, I think, was about 12 miles, so more like about 19 kilometers away. So, but it doesn't matter. This is what we're getting. And again, when we get rid of them, and I just drew this, all we see is two boxes moving up and down a line. You're not going to say that either one of these is not the same as the other. But when we see it like this, we'll see one disappear behind the horizon and the other one rise up. But they're the same thing.
Yep. Nope. Great presentation, man. Thanks for coming on last week and this week to do this for us. I know we greatly appreciate it. I know you do dope presentations, and I'm glad to see it evolve over the time that you've been building it.
Yeah, well, I've actually there's one more part to this where I will, where I can start introducing, so I got it here, where I can start introducing what I am saying is actually going on and how we can form an entire working model from this. This one, I think. Okay. So in a sense, imagine here, and we can go over this another time in a much deeper presentation.
Look at all these slides. Another 2,000, it looks like.
Yeah. Yeah. Okay. So we go here and we look from here and we go, okay, so here we have someone who's approximately 100 feet high. This is their cone of vision. This is their circle. This is what they can see. Right? We move to someone who is, okay, so sorry, there we go. Now someone's sort of more like, over 400 feet high. Their cone of vision is further. Right? Then we move to someone, is that okay? Someone who's much higher again, and their cone of vision is bigger. So then prospectively, what we get is this happening. But each one of these is actually zero. It's just that the person over here to the very left, who's down low, will see it start to disappear there. The person who's up really high, obviously they can see the horizon further away. So what they're going to be doing is seeing that continue. The person who's at the lower level, that boat's now disappearing for them. But if there was someone in the middle there, they would be seeing it come down and go up again, right? So to cover the same distance, so now the next person, they'll be now watching it go up higher again. And this is all basically still staying on one level plane, but each person over the entire plane of the Earth is seeing it differently.
That's really cool.
So the person way over here to the left isn't going to see this anymore. This disappeared here. But now a person here will see this go from there to there. Or if there's someone here, they'll see it go here to here. Then it will start to disappear. Now this person will see it go from here to here. But this person up here, he will see it get all the way to this point. It's still all on zero. But what it's always got to do is it's got to climb up within your perspective grid, and it's going back down within your perspective grid to zero. But once it gets from here to here, it's so far away from this person now that the angular size is so small, it's just going to keep reducing in size, but it's going to keep appearing like as if it drops further and further away. So we can actually come up with an entire working model through this.
Like how you demonstrate it at every elevation. But like, so not for nothing, but that circle you drew in the middle, that cone of perspective, that's exactly what the Globers argue, which is why we see what we see. They take this cone and they move it around this sphere, and it always looks as though your sphere of infinite horizon at your 3 mile moves with you, and that's how they justify all the same observations. But it's just, it's useful to point out why perspective alone is enough to explain this, so that the mystical Earth curve explanation can be withdrawn from this from this coupling that they gave it with basic perspective.
Yeah, exactly. So each observer here can only see to the horizon. You can't see past the horizon. Again, because no matter how high you go, the horizon is the furthest visual point you can see the surface. And when we get these, I mean, most of the time when you're up in a plane, the horizon is just fuzzed out. And even if we were to get out an infrared camera, okay, that's still going to get further, but that still doesn't mean that you're seeing as far to the horizon as it actually is.
And then we get back
Just
to the
continues
world
to go.
of incoherent Rayleigh scattering. Yeah, totally.
Yep.
So yeah, we can actually design an entire model on this now, which is what I've called the horizon perspective model.
Coming, not
Because
calling
everything
it
you see-
the plain reality. Come on, man, that's right there.
the plain reality. And so this is kind of really where you are. You're in this basin. So perspective is really going like this. It's not going up. It's obviously going, everything's coming down towards you. So you're seeing like that, everything going up. That's how you're seeing.
Yep. So the distance to the horizon is a specific and direct function of observer height.
Yeah.
That's the
and
crux of it.
refraction. The refractive conditions of the day will give you how far the horizon will be at any given moment, which can change from moment to moment. And your height is what creates the horizon in the first place. And obviously, the higher you go, the bigger that spread, the further you will see. But you will still have refraction affecting you. And some people can, I don't have it here, but even when you go up to like 1,000 feet, there's a Canigou one where you see an inferior mirage, where Mount Canigou's an inferior mirage. So even getting up to 1,000 feet, we're creating inferior mirages. So I've got some observations that I could do from about 2,500 feet, but that's probably more like about a 30K drive away from me. So if I try to do that on a regular basis, it's going to be a bit of a journey. But I might try and get some of those in the morning to see if I can get inferior mirages. And so if I can get an inferior mirage from 2,500 feet, or I think it's closer to 2,700 feet, it's just showing you that even when you're looking up really high and looking down, the inferior mirage is upward bending light, right? It's upward refraction. Well, they're saying that the light is always bending down. And if you're up higher, you're looking down through denser and denser layers. That should be bending the light downwards, right? So how are you seeing an inferior mirage? Because an inferior mirage is upward bending light. That shouldn't compute. They're not like those two things shouldn't go together.
They're not
You can't
afraid
have
of
downward bending light
paradoxes.
and upward bending light at the same time.
If it supports the globe, I certainly can. I have no qualms about that.
No, I like it when globies try to assert that anything going on concerning refraction in the distance is actually serving to help them see something more clearly when it's all about distortion.
So let's see if we can find it, because it's Mount Canigou, isn't it? Just put in Canigou. Let's put in Mount. I don't know. Is that spelled right?
I'm sure I don't know.
Can't read it. Canigou.
Yeah.
Canigou. Canigou.
Yeah, but no, I'm just getting all these close ones. I'd have to put in from whatever that observer point is, wouldn't I? No, so can't do it. I was going to see if I could find that one where you can see it in the inferior mirage. Ruhif's presented it before, not really even noticing that it's an inferior mirage. And when you see it in the inferior mirage, you see less of it, and that's the one that he likes to use the most, the one that's in the inferior mirage. So you actually see less of the tops.
Yeah, and if you ask him about how much she should be seeing, he says, "Who cares?" That's the real position.
Yeah.
But yeah, great stuff, man. Great presentation, great everything last weekend, this week. I think this is one of like the crux of the arguments with the globe Earth, is that ships over the horizon. I think we've so justly argued against that they should move something else. But if you took 3 hours and explained all this to all the globers that you argue with, the next day you'd come back and it'd be like none of it happened, and they'd say the same thing. They'd make the same argument.
Yeah, well, I think the next thing is to do this on Discord, so then we can get them all coming in and they can do their attacks on Discord.
I'll tell you,
And we
man.
can
You should set up a prez on Geos and Earth Awakenings and just invite them all, and then they'll all come and do their stuff and be led by Ruhif. and you probably have a good time.
Yeah. Well, I'm sort of in talks with Geo at the moment. We'll get it sorted out at some stage.
Nice.
We'll
So
get it done over there.
I don't think we'll have GlobeBusters next week, everyone. I think Alan's internet, it may or may not be in the process of being created and or extended. But so that means it won't be here on the 12th, but maybe by the 19th we'll be back with my press for dams.
That sounds like a safer plan for sure.
Yeah. So what? No one's got any questions still?
No, a Glober came to the chat and everyone got distracted. And the Glober's main question was, does the horizon rise to eye level or not? So one of the basic principles that you put to bed in the beginning, and then, you know, someone who doesn't watch will just come in. And now everyone's trying to convince that one person. That's how.
Yeah, the other straw man question there is, so I rise to the horizon without moving?
Yeah. No, eye level above the horizon is what we're talking about, right? So that's what gives us the apparent. That's what gives you the dip correction. That's what gives you everything.
Yeah. So if you see here, all this just kind of looks pretty natural, right? But this one I put in, this one's real. And this little sailing boat over here I put in there. But prospectively, this is just how we see. There's some other good, like I've got a lot that I can do. I'm going to start dropping a lot more videos now onto my channel. So now that I've got this, I'm going to start putting all this onto my channel. I'm going to start doing a lot more videos so people can have ammo. I've got to somehow break this down into 2 or 3 minutes. I'm going to, I'll probably get ChatGPT. I'll use AI to do that.
Take 4 hours down to 2 hours, down to 1 hour, down to a half an hour, down to 10 minutes, down to 5 minutes. So you finally get your YouTube 2 minutes short. That's the progression you got to go through.
Yeah, exactly. So, you know, we see all these boats all just sitting there appearing to be below the horizon. This is kind of what I was presenting before when I first started introducing it, showing all this stuff. We see those ones back there below the horizon.
Although, you know, not for nothing, but this particular argument is where I would never argue with Globers. Like, you're going to go do a presentation and try to take on all comers, and I have nothing but respect for that. But me personally, I won't even argue service level observations with them because they just, it's almost the observation to work for both models. Whether they say it's Earth curve, they're just going to say that. Whether we justify it, substantiate it, show how perspective works, quantify it with, no matter what we do, they're just going to say that that's Earth curve. So like, there's nowhere where that any service level observation will convince anyone from either side of anything. That's just where I'm at with it.
Yeah, I totally get it. And I agree. I know that they're just going to gaslight it and not really going to, they're not going to be honest about it. They are going to be disingenuous about it. That's just what they would do. But pretty much, I think if you haven't realized that this whole situation is now technically put to bed, this is just how we argue it. What's going on here? Why is this below this? That's all there is to it. And, you know, it's like, it's not something that's, you know, it's not just an occasional thing, you know, it just happens all the time. It's just how we see. And it won't matter where you go in the world. This is just how we see. So it's not like anyone could say this is exclusive to me here in my area. It's not exclusive to me. Everyone could do this. Everyone could go do this.
Yes, but none of the armchair cowboys will actually spend the effort. We all know the truth there.
No, but also anyone who's done the observations in the past, just go look at your observations again. So everyone who's done them, you'll see that this is exactly what's going on. Everyone can show it. Everyone can point this out and go, yep, look, here we go. This is me here in this spot in America. This is me here in this spot in Norway, whatever it is. And look, we're seeing the same thing. It's never going to change because that's just how we see. It's your height above the surface. That's what's creating the horizon, and refraction is creating the distance to the horizon. And everything as it goes towards the horizon will rise, and when it moves away from the horizon, it will fall. And that happens on either side.
Nice. All right.
Anyway, I'm sure it's time to go.
Try to wrap it up. Yep. Let's see what we got for any more questions. Nope. Everyone's still trying to take turns at that one Glober. Boy, you guys are really easy, man. Easily distracted.
Triggered.
Yeah. It's well, I mean, it's kind of like we sit around waiting for the one Glober so we can all get them.
Yeah. Well, that's what they do. I mean, you know, like when I jump into when I was on Earth Awakenings the other day, it's just like, Rah! Ph.D. Tony was there, so it was good times.
Yeah, I can't stand that dude. So it's a travesty if I go there and I'm like, oh, I gotta listen to Tony. Whew.
Yeah.
But yeah, all right. So we'll wrap it up. Thanks again for coming, dude. This has been super great presentation. And like I said, we will not be here next week, the 12th, but we will be back on the 19th, hopefully.
All right. Thanks for having me, guys.
Great. Thanks, everyone. Thanks, Stone.
Thanks for coming,
panel.
man. That was awesome.
That was fantastic.
See you guys next time. Thanks for coming by.
See you in a week.